So, given an equation in x and y, each piece of the graph that satisfies the vertical line theorem implicitly defines y as a function of x. It's not explicitly saying y is equal to something in terms of x, but implicitly we get y as a function of x. This means we can apply calculus, for example differentiation, to the equation that defines the curve. So, when we take the derivative of an expression, for any time that we take the derivative of an expression in y, for example, if part of my equation involves a function of y, we have to apply the chain rule. So for example, if I'm taking the derivative of a function of y, I'm taking the derivative with respect to x. Well, the derivative with respect to x of f of y is f prime of y times y prime, because y I'm thinking of as the inside function. Take the derivative of the outer function, apply to the inside, then I multiply by the derivative of the inside function. Okay. All right, let x squared plus y squared be equal to 1. This is again the unit circle centered at the origin. First, let's find y prime. So what we can do in this implicit differentiation is we can take the derivative of both sides with respect to x. So I'm taking the derivative of x squared, of y squared, and of 1. Now the derivative of x squared is just, by the power rule, 2x. The derivative of 1, since it's a constant, is equal to 0. The hard part is the derivative of y squared, but I'm thinking of y as a function of x. So the chain rule says I just get to take the derivative as usual. Y squared, its derivative, according to the power rule, is 2y, but since y is also a function of x, I have to multiply by the derivative of y. So I multiply that by y prime. So whenever I take the derivative of something involving y, I have to multiply by y prime. That's just the chain rule. Okay, so now I have an equation that involves x, y, and y prime. But I just want y prime. So what I'm going to do is solve for y prime. Okay, so I've got 2x plus 2y times y prime is equal to 0. This is really a linear equation in y prime. So my first order of business is to get everything involving a y prime on one side and everything that does not involve a y prime on the other. Specifically, anything that has a factor of y prime should stay on one side, everything else goes on the other side. So I've got 2x over here, there's no y prime, so I'm going to subtract 2x off to the left-hand side, or right-hand side. That leaves me with 2y times y prime is equal to negative 2x. Great. Y prime is now a factor of the left, and there is no y prime on the right. So now I'll divide by whatever's in front of y prime, which is 2y. I divide both sides by 2y, and that gives me y prime is equal to, I cancel out these 2's, and I get y prime is equal to negative x over y. Okay, so now let's apply this. Let's find the equation of the tangent line at 3/5, 4/5. Now let's notice that when we get the equation for y prime here, it's not just in x, it also involves y. So if I'm going to find the equation of a tangent line, generally I'm going to not just give you an x value, I've got to give you the y value too. That's because generally a single x value in one of these equations is going to give you multiple y values. For example, if I took x equal to 3/5 here, both plus and minus 4/5 could be a possible y value that gives me a solution to this. So I'm specifying 4/5. So to get the equation of the tangent line, I need the slope. Y prime is going to be negative 3/5 over 4/5. That's x over y. That simplifies to negative 3/4. Then I plug that into the point slope form, and I get y minus 4/5 is equal to negative 3/4 times x minus 3/5. And here is a graph of what's going on. Let's just notice that this is a negative slope. This curve is this tangent line is decreasing. Also, the slope in magnitude is about 3/4. Its absolute value is 3/4, which means that it's close to 1. This line looks like it has a slope close to negative 1, so that seems to corroborate this. So great. Okay, so let us do another example. Let's take x cubed plus y cubed equal to 6x times y, and let's find y prime. Well, the first step we're going to do is differentiate. To differentiate x cubed, that's just 3x squared. To differentiate y cubed, I have to apply the chain rule. I take the derivative as normal, and I get 3y squared, but then since I'm taking the derivative of something involving y, I have to put a y prime there. That's really, again, just the chain rule. On the right-hand side, I have 6xy. I'm going to interpret this as the function 6x times the function y. I have to use the product rule. So I take the derivative of 6x, which is 6, and I leave y alone, so I get 6y. Then I add, leaving 6x alone, and I take the derivative of y. Well, the derivative of y is 1, but the chain rule says I have to multiply by the derivative of y, or multiply by y prime. So I get 6x times 1 times y prime, that's just 6xy prime. Great. So now I'm going to put the terms with a factor of y prime on the left and anything that does not involve a y prime over to the right. So I've got 3x squared plus 3y squared y prime equal to 6y plus 6xy prime. That means I have to subtract 3x squared from both sides and subtract 6xy prime from both sides, which leaves me with 3y squared y prime minus 6xy prime equal to 6y minus 3x squared. Now everything on the left has a factor of y prime, and I can pull that out so I can solve for it. I factor out the y prime, giving me 3y squared minus 6x quantity times y prime equal to 6y minus 3x squared. And now to get y prime by itself, I'm going to divide by this factor, 3y squared minus 6x. This leaves me with y prime equal to 6y minus 3x squared divided by 3y squared minus 6x. So here is our first question. Let's let x cubed minus x squared y minus xy squared minus y cubed plus y be equal to 0. First, find an expression for y prime. And second, find an equation for the tangent line at the point 0, 1. Let's remember, I already drew this curve for us. This was the sort of S curve. So maybe that'll help you interpret your answer to part B. Generally, when we do implicit differentiation, y prime ends up being a fraction. So we're often interested in finding out when a curve has a horizontal tangent, and also here we might be interested in when a curve has a vertical tangent. Well, it turns out that we're going to have a horizontal tangent if the numerator is 0, which means that y prime is 0. A vertical tangent if the denominator is 0, which really means that we're dividing by 0, so in a sense, y prime is plus or minus infinity. And well, actually, what happens if both are 0? Who knows? It's hard there. And we're not going to get into that sort of thing, so don't worry. Okay, so let's try this example. X squared plus xy plus y squared equal to 3 actually is the equation for an ellipse. It's not the standard sort of ellipse form. This guy is actually going to be an ellipse, sort of at an angle. So let's find the horizontal and vertical tangents of this ellipse. First, we're going to find y prime. I take the derivative. The derivative of x squared is 2x. The derivative of xy, I have to apply the product rule. The derivative of x is 1, so I'm left with just y. I'm going to leave y alone. Then I leave x alone and take the derivative of y, which gives me y prime. And then I take the derivative of y squared, which gives me 2y, y prime, and the derivative of 3 is 0. I get everything with a y prime is already in the left, so I'm just trying to get everything without a y prime onto the right. So I subtract 2x and y to the right side, giving me x y prime plus 2y, y prime equal to negative 2x minus y. Now I factor out the y prime, and I divide by this term to get y prime is equal to negative 2x minus y divided by x plus 2y. Now to find the horizontal tangents, that's going to happen when the numerator is equal to 0, because then the derivative is going to be 0. So that is when negative 2x minus y is 0. And you can solve that and get y equal to negative 2x. Well, what do I do with this? I have some more information about x and y. I know that they satisfy this equation right here. So I'm going to plug y equal to negative 2x into the original equation. I get x squared plus x times negative 2x plus negative 2x squared equal to 3. I simplify it, and that gives me 3x squared equal to 3, which I can solve and get x equal to plus or minus 1. How do I find y? Well, this equation right here also tells me how to get y from x. So y is equal to negative 2x. I plug in plus or minus 1, and that gives me y equal to negative or positive 2. So the horizontal tangents occur at plus or minus 1 and negative or positive 2. Now to find where the vertical tangents occur, I set the denominator equal to 0. A very similar analysis to what we did before gives us y equal to plus or minus 1, and that gives me x equal to negative or positive 2. So that gives me my horizontal tangents at negative 1, 2, and 1, negative 2, and vertical tangents at negative 2, 1, and 2, negative 1. And there is my ellipse.